I'm Jack Holt, for anybody who doesn't know me yet, recent new faculty here. And happy to introduce our speaker for today, our own DellaGiustina. She, a little background, Danny received her bachelor's in physics from University of Arizona with a minor in planetary science. And then she went on to University of Alaska at Fairbanks and got a master's in computational physics. And then she came back to LPL, and she's worked on quite a variety of things. As an undergraduate, worked on thermal metamorphism and asteroids, and did lab work, and then at UAF, she worked on ice sheet models and did field work for glaciology. And the ice sheet model that she helped develop is actually widely used now and is even used by a collaborator of mine on Mars glacial modeling. And then here she's the lead imaging processing scientist for OSIRIS-REx, working on photogrammetry and all sorts of image-based observations. But today, she's actually going to be talking about something that's completely different, work that she's been doing to plan a seismometer for Europa, and including fieldwork in Greenland. Titled The Seismometer to Investigate Ice and Ocean Structure, Greenland Analog Mission. So let's give Danny a warm welcome.
Thank you, Jack. All right. Yeah, so I think many people in the department know me through my work with OSIRIS-REx. So today I'm going to talk about a project I've been working on. Feels like I've been working on it on the side for a little over 2 years now. But it's finally beginning to take up a little more of my time. And we just finished our second out of 3 potential analog missions in the cryosphere for examining how we might perform seismology on Europa. And so I'll just acknowledge that this is definitely a team effort, and 2 of my team members, Hop Bailey and Veronica Bray, here at the U of A, have certainly had a big hand in the success of this program. Okay. I'm trying to advance the slide. Here we go. All right, so what is the seismometer to investigate ice and ocean structure? And our acronym is SIIOS. Well, it's kind of 2 parallel efforts. The first is an analog mission program that's been funded through NASA's Planetary Science through Analog Research, or PSTAR, project. And it's involved 2 different field campaigns so far, one at Volcano Glacier in the Delta Range of Alaska, and one in northwest Greenland on the ice sheet over a subglacial lake. It's also, in parallel, an instrument maturation effort. And really our goal as part of this instrument maturation effort is to develop a seismometer, a seismic instrument that could be eventually included on a landed mission to Europa. And in fact, we're kind of expanding out now. We're also very interested in building a seismometer that could be deployed on the moon as well. So today, this talk is mostly going to focus on our recent field campaign in northwest Greenland. But I'd be happy to talk about any of these other elements of the project offline. And so how did this project get going? The motivation really came from a meeting that we had as a department about 3 years ago, where we were discussing this upcoming Europa Lander mission that there's been a handful of concept studies detailing. And so here is the 2012 report, and then the more recent 2016 Science Definition Team study, examining what you might do on a landed mission to Europa. And in both of these studies, the payloads, the baseline payloads, have included a seismic instrument. And so our department has a really long history of building spaceflight cameras, and kind of the most obvious thing that came to mind is we should build a camera system. But my colleague Hop Bailey kind of threw out the idea that, well, maybe we should also put together the acoustic instrument. I think it was called an acoustic sounder in this 2012 report. And basically nobody latched onto that except me. And the reason I latched onto that is because I once hauled seismometers around the Greenland ice sheet, and I thought that was a lot of fun. And I saw this as a potential avenue to get back into the field. So the objectives for the seismic instrument has varied a little bit in various, in between these studies and also various community reports. But these are kind of the common themes. We want to measure the depth of the ice and water layers for Europa's internal structure. We probably will want to determine what the proximity is to any intermediate bodies of water as well. And we want to begin to constrain some of the properties of the ice shell near the landing site. And so with that, looking at these objectives, we decided that U of A and LPL should be the place that we should be the institution that builds this seismometer. And this is also motivated by the fact that there's not really, at present time, any US institution that can build seismic instrumentation that's spaceflight ready. So we want to do that. And like I said, also fieldwork is a lot of fun, and I saw this as a potential avenue to being able to accomplish that. All right, so what was it in those studies that kind of motivated this idea that a seismometer would be a valuable payload on a Europa Lander? Well, there's a handful of ideas about what sort of seismic events we might see on Europa, and a lot of them are motivated by the kind of the terrain of Europa, where we see a lot of chaotic terrain. We might see evidence of ridge building. We see cracks that have appeared to have undergone dilation and also contraction, maybe even subduction of surface materials. And a lot of this evidence has come from the imagery from the Galileo mission. Also in the past couple years, there's been accumulating evidence that Europa has active plumes. And so one potential source of Europa quakes be tidal cracking, and observations of these transient plumes, including 2 sets of data from the the Hubble Space Telescope STIS instrument in the far UV, have indicated that we do see evidence of these transient plumes. A modeling study by Roden et al. In 2015 was able to link these observations to opening and closing of cracks that are modulated by tides, as long as you also take into account not just the tidal stresses on Europa, but the spin axis and potential obliquity waves. And so it seems like we're beginning to tie together as a scientific community a consistent story that Europa is experiencing these tidally modulated cracks, and that this could potentially lead to a seismically active Europa. But we need a little more than that in order to build a payload and send it on a spacecraft. And so some more detailed studies have been building a case for this. And so I'll just quickly go through the salient points here. We can look at tensile cracks, and in particular, potential normal and strike slip faults from imagery and photogrammetry. And we can look at the geometry of these faults and estimate what the maximum size event or earthquake could be triggered from these faults. And so the current best guess from what we've observed is that you might see a moment magnitude 5.2 quake on Europa. And as a potential analog, we also see really deep moonquakes that are related to tidal stresses that are around moment magnitude 3 on our own moon from the lunar Apollo data. And we know that the tidal stresses on Europa are somewhere between 8 and 20 times larger than on our own moon. So if we're seeing some quakes related to tidal stresses on the moon, then that might help us build the case that they could exist on Europa. there was a study done not too long ago looking at what the flux of meteoritic material might be at Europa and whether or not we could expect any impact-related seismic events. And the answer is probably not, at least for an instrument that's deployed for less than 1 year. And so it's likely that we might see some events related to faulting and ice cracking, and maybe even some deeper events that are related to the deeper interior flexing as a result of tidal stresses. But then that also gets to this other question of what we might expect the seismic noise to look like at Europa. And so for folks who aren't super familiar with seismology, we kind of refer to seismic noise as the smaller events that accumulate and create this kind of background seismicity that larger events would need to exceed in order to be detectable. And this is an area of very ongoing research. There is probably the best paper I've seen on it is something that's still in review. But one paper that makes a couple of assumptions, leans a lot on how seismicity, leans a lot on terrestrial seismicity to come up with some predictions, has estimated that the noise, kind of the background accumulation of small events of Europa, is going to be quite a bit less than on Earth. So these two curves right here bracket what we call the new high noise model for Earth and the new low noise model. And so it's within this range that we expect most events on Earth to pop out against. And right here, this curve and the yellow probability, the yellow to blue probability distribution behind it, indicate where their model seemed to land on what the mean was for a European noise profile. So we don't know, but models are getting better and better at pursuing this work. And even if we didn't have a lot of background seismicity on Europa, it might beg the question that why wouldn't we do an active seismic experiment where we produce a source instead of relying on the innate seismicity of the planet, or excuse me, of the planetary body. Renu?
Where would the moon lie on this?
Oh, the moon is very quiet. So the moon would be probably down here between -3 and -250 decibels. Okay, so now that we've kind of convinced ourselves that there's going to be seismic signals on Europa that we could use to perform passive seismology, we can get a little into the Europa Lander mission concept that has been the impetus for us proposing to do this work that we've been conducting over the past 2 years. Okay, so the goals for the overarching mission are first to search for evidence of biomarkers and/or signs of extant life. So a seismometer is not going to help you do that, but it does help with maybe these second two objectives. The second is to assess the habitability of Europa via in situ techniques that are uniquely available by means of a landed mission. Certainly detection of the ocean on Europa and also constraining the crustal thickness really help us assess habitability, because they allow us to figure out how close sources of liquid water are to the surface, which is going to be rich in oxidants because it's constantly irradiated. And then also characterizing surface properties at the scale of the lander to support future exploration. So we will be able to constrain seismic velocities, which are a great proxy for temperature and also anisotropy in the crust beneath the lander from a seismic experiment. The time frame for this program is a 2025 launch via SLS. So this depends on the success of the SLS program, and sometime in the early 2030s for Europa surface operations. The mission, as it's currently proposed, would be battery powered. And so this leads to a very short mission duration. Right now proposed at only 20 days. And the notional baseline payload, along with the broadband seismometer, includes color stereo cameras, a gas chromatograph, a suite of microscopic instruments along with a fluorescent spectrometer, and also a drilling and sampling system to feed things to both the microscope and the gas chromatograph. Okay, so within that, what have been the objectives that have been outlined for a seismometer? So as per the 2016 study, there is kind of 3 main objectives that were mapped to a seismic payload. So these are the objectives that the seismometer could help us address. And the first one, and I'm just going to read the portion of the objectives that corresponds to how the seismometer will help, or how the seismometer will allow us to fulfill these objectives, is first to determine the proximity to liquid water. And so obviously understanding how far we are from the ocean, the depths of the crust, allows us to do that. And the second is to observe the properties of surface materials, which I spoke to earlier. Figuring out the seismic velocities really will allow us to constrain several aspects of the structure and also maybe any internal layering that we're seeing beneath the lander. And also connect local properties with those seen from flyby remote sensing. So for example, if we detect a large event and then we see something like a crack dilating on the surface of Europa, can we temporally link those two together? And this third objective is to characterize the dynamic processes of Europa's surface and ice shell over the mission duration. So looking at the rate of seismic events as a function of time across a 20-day mission is going to allow us to begin to quantify how geologically active the Europa is. So over here I have a plot kind of demonstrating how we might expect a plot called a seismogram to look like when we consider the structure as we currently understand it of Europa. So we assume that there's an ice of some thickness, and I think we assumed a 10-kilometer or 20-kilometer thick shell in this demonstration. And then an ocean, a liquid water ocean, and some sort of silicate interior. And if we had a little group of earthquakes, we would expect to see reflections from a couple different places. In particular, at this ice-water boundary, and then potentially from the ocean base to the silicate interior. I'm going to focus on these ice reverberations because these are really, really interesting. So on the seismogram, we have slowness, which is, you can think of it as the inverse of velocity. So something with a high slowness is going to be slow, or have a low velocity. And then the seismic travel time, so how long it takes for these sort of phases to show up on a little seismometer that's sitting over here. And the thing that I want to point out is that these ice reverberations that you kind of see coming down here about 100 seconds or so, 50 to 100 seconds after these events, these get trapped in the ice shell. And as a result, looking at the characteristic frequency of these ice reverberations gives us a very good metric for determining the thickness of the ice shell. And so the seismic phase, there's a couple seismic phases of interest, but one is called a Crary wave. And we know that the characteristic frequency of a Crary wave is going to be inversely proportional to the thickness of the ice shell. So it is something that would be immediately diagnostic of the thickness of Europa. And that happens because there's just a very, very dramatic acoustic impedance contrast between ice and water. So you can kind of think of it in a lot of ways like for a characteristic frequency of wave, it becomes trapped in the ice shell, similar to total internal reflection that we see when we have optical fibers. Okay. All right. So we've reasonably convinced ourselves that Europa has seismicity, and we can use a couple of clever seismic phases to constrain some of the things that we're very interested in with a seismic payload. And so this kind of begs the question is how would we even deploy a seismic experiment on a spacecraft? It's only been done a couple times before, and it hasn't always been done successfully. So the Apollo instruments, the Apollo seismic experiments were quite successful. Those were done by the Apollo astronauts. Viking 1 and 2 were kind of the next step. Viking 1, the seismic payload on Viking 1 was never uncaged from its tether that was meant to keep it stable during launch, so it recorded no data. And the Viking 2 seismometer was deployed on the lander and not within a well-protected, well enough protected vault. And so it basically was a good wind anemometer. It measured the wind. And in fact, I was looking not too long ago at the data was recently put back into the PDS in a more digestible data format for seismologists to look at. And all of the preamble to looking at the data was talking about how is this really good for looking at wind on Mars. So it didn't necessarily accomplish its goal of constraining the interior of Mars. It maybe detected one event, and even that is a little debatable. So InSight just recently launched, and it'll be making its way to Mars soon. And InSight takes advantage of many lessons learned from Viking. It has a burial and leveling system, and hopefully will not encounter some of the same challenges. But that's not a lot of seismic instrumentation we've sent into space. And so I've just kind of gone through some of the ways that we know things are going to be different if we're going to deploy a seismometer on Europa, or really any spacecraft. So you probably only want to use one instrument. And this is because you might only have the mass allotment for a single instrument. That's certainly the case on the Europa Lander, which is severely mass constrained, because it's going to take a lot of energy to get to the outer solar system. And in terrestrial surveys, we don't always do this. In fact, we like to have different instruments that are sensitive over different frequency regimes. And so we typically deploy more than one instrument so we can look at a wide variety of seismic signals. We might only be able to deploy a small array if we did have more than one instrument type, or just a single instrument again. And so kind of what I'm getting at between these two bullet points is that for a single instrument, we might only be able to deploy one, but even if we were to set out a small array, and so in terrestrial experiments, seismometers are often set out at distances that are determined by the frequency of or the size of the wavelengths that we're interested in, and we're probably not going to be able to do that on a spacecraft. And so if we were to deploy more than one instrument, it likely might be the same instrument type, because it's hard to space qualify several instruments. And so we might set these things out, let's say, for example, at the three corners of, this was one iteration of what a potential Europa Lander would look like. The three corners or the three edges of the petals of this kind of Pathfinder looking lander. Or we're just gonna put one on our spacecraft, because that's all we can afford in the mass allotment. Another interesting problem that is something that I'll be talking about a little later on, because it's pretty germane to the Europa Lander, and hence has been something we've worked hard to understand in our P-STAR work, is what happens when you have to mount a seismometer on board a spacecraft. And so we know from Viking that cannot go well, and that might not go well if you have an atmosphere. Europa's atmosphere is very, very tenuous, if it exists at all. And so some of the same challenges might not be employed or might not be encountered, but we're still going to encounter other issues, because now we're convolving the response of our instrument with the response of an entirely different structure, and then trying to figure out how that couples to the ground and what that says about the interior of a planetary body. So this could be an issue, and you have to think very carefully about how you're going to do seismology if you're now mounting your instrument to a spacecraft instead of coupling it directly to the ground. And then, as I mentioned earlier, the probable use of only passive sources, because setting out an explosive is something that most NASA missions are not going to be super stoked about. Maybe a different agency would be okay with that. But anyways, and so I feel like I've motivated this point. We believe we have enough passive sources on Europa, we can get away with that. But so I feel like these 4 things do a good job of highlighting the specific challenges. Okay. So in our analog missions, as well as our efforts to mature a very novel optical seismometer that could eventually be deployed on a spacecraft, we've tried to figure out what do we have to do, what are the necessary questions we have to answer to make sure that we could meet the challenges on the last slide I presented. And so the first thing is having an instrument that is going to fit within the allotments of the Europa Lander mission, which means it has to be really small. It can't be small in form factor and also small, low in mass. We can probably only deploy one of these on the Europa Lander mission, so it needs to have a very broadband response. It needs to be able to detect a wide range of frequencies of interest. We're not sure what is going to, the terrain of Europa is expected to be pretty irregular, so how do we deploy an instrument on this very irregular terrain and ensure that it's going to faithfully record seismic motion along 3 separate components, which is the typical way that seismometers are often designed on Earth. You have a component in the vertical direction, and then one in the horizontal. You have 2 in the horizontal, typically one in the north and one in the east, and then if you have those 3 orthogonal components, you can kind of rotate them so you can look at the radial component and the transverse component coming out from a given earthquake event. And so with those things in mind, here we go. We've chosen a broadband seismometer, and we've partnered with a company called Silicon Audio that's based out of Austin, Texas, because they meet a lot of the criteria that I just mentioned. So this is the size of their seismic instrument. It has a very, very nice range of frequencies that it can capture. And so this is illustrated on this chart here where you see this self noise, which is a pretty it's a self-explanatory concept. It's just the noise that the instrument inherently makes. And so you need to, if you have something with a high self noise, then it will only be able to detect events above that noise as a function of frequency. And so right here, this is our current device in this red line, and you can see how that compares to the 2 InSight instruments. So this is what I was getting at earlier when I was talking about a single instrument type. And InSight, their SEIS experiment has 2 separate sensors. One is is a shorter period one, and so it does a little better. It provides a complement to the very broadband one, which is much lower noise, and so it might get flooded out by more ambient noise on Mars. So we have these 2 instrument types, but the very broadband is extraordinarily sensitive. So it might be good if Mars is much quieter than had been anticipated. And here is, so here is the very broadband. So you can see that the short period has a slightly longer tail on either side. So it's going to be able to record slightly lower frequencies, but at higher noise, and slightly larger frequencies, but also at higher noise. So as part of our maturation effort, we are trying to bring the overall noise of our sensor down further. And you'll see that this, you can recall the slide I showed towards the beginning of the presentation where we looked at the Europa noise floor. We really want to be able to be sensitive enough to capture signals for a quieter planetary body than Earth. So this gets into kind of the details of the instrument specs and what we're working towards there, but there's a lot of other things that need to be considered besides just the instrument specs and how sensitive the instrument is, because doing seismology on a lander is going to be challenging for other more operational reasons. Like I mentioned earlier, we need to figure out how we do this in-vault seismometer, how we deploy an in-vault seismometer in such a way that we can faithfully record the displacements that are occurring in the ground, though we're not coupled to it. And in fact, I'll skip over here because this highlights the things that I'll address in the talk. And then also, we want to assess the effectiveness of just using passive seismic signals for constraining crustal thickness. So this is what I mentioned earlier when I was talking about those phases that seem to be immediately diagnostic of ice thickness as reverberations. And so of our objectives, I'll hit on these three things as part of this talk. And some of the other items, like developing protocols and requirements for onboard generation of data products, and also how do you do extreme compression when you're downlinking data from the outer solar system, is stuff that that is certainly very important, but our program just hasn't gotten to it. Okay, so with all of that in mind, we've deployed some analog experiments at terrestrial sites, and I feel like the question that I get most often is, how can you even make this comparison? So I want to say right off the bat that we know that there's differences between Europa and the terrestrial cryosphere, and nowhere on Earth is going to reproduce the shape of the European ice shell, the expected seismicity, the temperature differences, although we can do a reasonable job of extrapolating to the sort of seismic velocities that we expect at much lower temperatures, like what we'll see at Europa. But there are sites on Earth that do have some of the things that will help us. And in particular, when I showed that figure earlier of a column of ice over water over silicate bedrock, there are plenty of places on Earth that exist with that sort of structure. And that will allow us to measure very similar ice reverberations to what I showed earlier that are going to be immediately diagnostic of ice thickness. And so that's basically what I'm saying here. Analog sites do exist with ice that's hundreds of meters to kilometers thick, and whose motion is modulated by diurnal tides. These include ice shelves. These include the ice shelves in Europa, or excuse me, in Antarctica. And also, there's been some work to show that even subglacial lakes, through GPS data, show some amount, depending on their size, of tidal variation, and certainly at a minimum diurnal variation in some areas. And the reason this is important is because the seismic, let's see, I just said that, okay. And so we had proposed missions at two key places. One was Volcano Glacier in Alaska, and the other was actually the Ross Ice Shelf in Antarctica. And NASA came back to us and asked us to please not go to Antarctica because it's very expensive. And so we replaced that field site with an area that we're calling Lake Europa, an unnamed subglacial lake that was discovered in 2013 in northwest Greenland. And so I'll quickly talk about our Volcano Glacier analog mission, although I'm not going to spend too much time on that. But there were some very key differences between this field site, which is a mountain glacier in the Delta Range, the central part of Alaska, and Europa, and in particular, the relative structure, the amount of ice versus liquid water versus silicate is just it wasn't a great analog. We did this field campaign mostly to help us kind of rinse out some operational issues, like how do you deploy a series of seismometers on a footprint that would look like a lander? And this isn't typically how we do things. There's a lot of cable management involved. What are the sort of things we need to do to accurately simulate a lander structure so that if we were to deploy seismometers on it, we're doing a reasonable job of mimicking the anticipated behavior. And we did this at the end of the melt season, so we were hoping there would be enough basal, a large enough basal layer that we would see of water between the ice and the bedrock, that we might be able to see that in our seismic data. But so far, not really. And so we were able to do some really cool glaciology and rinse out a lot of operational issues with this field campaign. But I don't know that it helped us as significantly as our Greenland work with answering some of the questions that I highlighted a couple slides ago. So I'll talk next about our Camp Europa in Greenland. So to get a sense of where our field site is, this is the North Pole, and we're about 800 miles south of that. And so there is, in the kind of the furthest west peninsula coming out of Greenland, our site is right here. And so I'll move to the next slide so you can get a better sense of where the lake is on this. Okay. So 2 slides ago, I kind of highlighted this area. This is just a bed map or an elevation map, so you can get a sense of this increased elevation. Here is the ice. And so right here, we have bedrock. And then within this little square is our lake. And this little set of red hatch marks outlines a rough shape as determined from airborne radar. And Camp Europa was planted directly in the middle of it. So we really wanted to ensure that we were going to be sitting over a column of that coexisting ice, water, and then bedrock. And we did our own snowmobile-based radar surveys, and we did seem to land right in the middle of it, although the shape of the lake has probably changed a bit from what's depicted here. I got out of the field about 2.5 weeks ago, so everything I'm showing is extraordinarily preliminary. But here's Camp Europa. Okay, so what did our experiment consist of? So we did a handful of things, but the portion that is most applicable to helping address the questions that I highlighted a few slides ago was our what I'm going to call our small aperture array. So it was a very small array of seismic instruments, and this plan view right here helps kind of map what we did to this picture of our team talking through something over our little experiment. So we, in an effort to isolate things from the atmosphere, we actually constructed an enclosure that we deployed a little mock lander within. We designed this lander to attempt to faithfully represent what we would expect a lander spacecraft to look like. And we actually were able to do some finite element modeling to get a sense for how the response of this little lander structure would react to incoming seismic signals. It's been interesting looking at the data because the simulation didn't quite get it right. And so teasing out why that happened is going to be something that I'm working through for a while. But we had within our enclosure, which is denoted by the blue box here, 4 of our flight candidate instruments. So these are these little gray circles on each side of the enclosure. The entire enclosure was buried under well, we dug out about 1 meter so that we could completely fill in the entire enclosure with snow and just do as good a job as possible isolating it from the atmosphere. And so it's not depicted here because I want to illustrate where the lander is, but eventually there were different different supports put on here that closed up the structure. And so within the enclosure, we have our little mock lander, and then we had 4 seismic sensors, 1, 2, 3, 4, placed on the lander to do these comparisons with the on-lander seismometer and the sensors that we've buried in the ground, which is the more traditional way of deploying seismic instrumentation. And then beneath the lander, so you can kind of see one of them here, we had 3 instruments, including a little gray one right here, that's our flight candidate, that were meant to help us kind of calibrate what these guys are seeing versus a seismic sensor that's deployed directly coupled to the ground and in very close spatial proximity to the rest of the sensors. And so we, along with the flight candidate sensors, which, as I mentioned before, are these little gray ones, we deployed some more common seismic instrumentation. So these little orange squares here are geophones. And then we also had one really large, really expensive broadband seismometer that would kind of serve as a standard for what we're looking at. Unfortunately, it looks like the big standard seismometer did not do very well in the cold. So it's been really interesting combing through this data over the past 2 weeks. So that's the layout of our experimental configuration. And what I'm going to talk about now is basically what I've had time to do since I got the data, which is quantify the difference. It's getting at this particular objective, which is quantifying the difference in scientific return between a seismometer that's in direct contact with the ice or coupled to the ground and one that is in the lander vault. Okay, so this kind of leads to the first question that I would like to answer, which is, on-lander seismology going to be viable? And so I'll start running through some of the data. And in fact, I'll advance through this slide pretty quick. So in the next couple slides, we're going to be looking at the 3-component seismogram of an event that happened on June 4th, and actually there's a typo there. It should be 22, so at 10:49 p.m. UTC. And this event occurred in the southwestern corner of Greenland. Now remember, our field site is up here, so it's about 1,000 kilometers away. And as I mentioned before, we can have 3 components, and they're usually oriented, of course the vertical is just up, but north and east. And then when we have those, we can just rotate them into a radial and a transverse component. So radial being radial, just the direction coming directly from the event to our stations, and transverse being perpendicular to that. And so what we're looking at here is the in-ground sensor that's buried beneath the lander. And so this probably provides a slightly more, a slightly better visual cue. So we have these 3 stations, or 3 sensors that are buried beneath the lander right here. And that's what we're looking at. And this is just the seismogram of that event, of that earthquake that happened in southwest Greenland. And so just a couple things to note. This looks pretty typical from my perspective, but if we look at kind of the range of values along the y-axis, we can see that they're all pretty comparable. So right here we're at 1.5, here we're at 2, here we're at 2, and these are all raised 10 to the 4th. But we're seeing amplitudes that are pretty similar along all 3 axes, all 3 components. So now let's go ahead and look at what happens on the lander deck. So first off, and maybe not everybody would see this, but this is something that pops out to me immediately, somebody who spent a little bit of time looking at seismograms. There's this kind of like ringing that we now see in the vertical component. And so this was the sensor that's deployed in the very center of the lander deck. And so it's this guy right here. And you can see that there's a little bit of a drumhead effect, which makes sense. The central part of the deck is probably experiencing the most flexure. And that was something that was predicted by our FEM analysis that we looked at when we were building this thing. And so you kind of see this ringing as it goes and then kind of slowly attenuates out on the vertical component. The other thing to notice here is we're now partitioning energy a little different between our three components. So here now it looks like we've transferred more energy to the vertical component and we've dropped a little bit, not very much, but in our horizontal components. So the interesting thing here is that we predicted this. We predicted if you deploy a lander at the center where there's going to be the most flexure of your little spacecraft deck, you're going to see something like this. We didn't quite get the energy partitioning right, but what we also predicted is that if you deploy something at the stiffest joint, which in these 4 joints were in our model all the same stiffness, then you're going to do a lot better. And so here is the seismogram for this sensor, which is right here, deployed at that stiff corner joint. And we see much less ringing compared to the other one, which is nice. Still a little bit of difference here between, we seem to be amplifying signal, again, in the vertical direction, and attenuating it a little bit in the 2 horizontals. So why does this matter? Well, if we're going to deploy a seismometer on a spacecraft to Europa, we better really, really characterize the response of that seismometer versus an in-ground seismometer or a well-coupled seismometer, because the partitioning of energy might not, that we see on our seismograms, it might not be coming from the source. It's coming from the convolution of our instrument response and the structure of the spacecraft with the source. And that just kind of, this highlights that a little bit. So right here on this slide, I probably should have put this on there again, but that's okay. Now I'm comparing this set of seismograms that we just saw with the one beneath the lander. So here and here. And so for this same event, you can get a good sense of how the amplitudes are changing between the different components for the on-lander sensor, even the one that's mounted to the stiffest part of the structure, and the in-ground. And so it's by about a factor of 2, we see an increase in the amplitude on our lander deck for the vertical component, and we decrease by roughly a factor of 2 for our 2 horizontal components. So this is certainly, looking at this sort of data is going to help us build a plan for what you have to do in terms of testing and verification and validation if we were to get an instrument, if we were to put an instrument on a lander spacecraft. And then a more effective way, I think, of visualizing or quantifying some of the differences that we're seeing between these 2 seismograms of the same event is to look at the coherence of those signals. So right here, I've plotted the coherence. And for those of you who don't remember coherence from digital signal processing, it's a metric that we can use to, the signal is reasonably well behaved, quantify to what extent a signal can predict the outcome of another signal. And so just kind of as a rule of thumb, anytime I see coherences that are less than 0.2, I don't believe them. So when I plotted this data, I was interested in saying, does it plot above 0.2 for this earthquake that we were examining earlier? And so in blue here, we have the coherence between the in-ground sensor and the lander deck sensor mounted on the stiffest part. So that is right here in blue, the coherence between this seismogram and the seismogram from this sensor. And we see that it's reasonably coherent. It's above 0.5, which is nice to see. That made me happy. And then we see that it begins to fall off at higher frequencies above about 10 hertz. And that was a little disconcerting because we designed our mock lander to have resonance at about the 100 hertz mark. And so I would have hoped that we could kind of see this really, really well-behaved prediction from one signal to the other out a little further. But in the end, we're still doing pretty good in terms of the overall coherence. And then even our central sensor that experienced a little more flexure, and we saw that ringing behavior, even that remains pretty well predicted by the in-ground sensor. And so that's that orange line right here. It doesn't do quite as well at the lower frequencies, maybe does better at the higher frequencies. So I'll be looking at the coherence between these two sensors and the in-ground sensor over the next, probably over the next several months. I made this plot yesterday, so this talk was a really good impetus to start digging through the data. But the point is that is on-lander seismology viable? Yeah, probably. It probably is. So that's good because that's what NASA's planning to do. They're planning to mount a seismometer to a lander spacecraft. And I'm not sure that they have a good sense of how are we going to then subsequently verify that we're doing a good job and we can achieve our seismological science objectives. This was just one other quick plot I put together, again looking at the three sensors that I have been talking about, the in-ground beneath our lander and the two on our lander deck. And this is a plot of the power spectral density. So that just gives you a sense of where the power is distributed across a range of frequencies for a given signal. And so this would be our in-ground. This is, again, our central lander deck, the one that experiences a lot of flexure. And this is our lander deck on the stiff part. And we're seeing that there's slightly different amplification of, which pairs well with what we saw in our seismograms. But in general, the relative power spectral densities for each looks pretty good. So that just gets again to our probably. It's going to be necessary to quantify, so that this kind of gets to the work to go now that we've just did a cursory check, we believe our results. It's going to be necessary to quantify the response and the self-noise of this combined lander sensor system and compare those results to in-ground sensors through modeling. And kind of the next thing on my plate to do as just a cursory check is to constrain the depth of our subglacial lake using both the in-ground and the on-lander sensors, using those ice reverberations that I talked about at the very beginning of the talk, and then comparing those results to external measurements that we got from ground-based ice-penetrating radar. So with that, thank you guys for your time. This is a picture of our field crew on the demobilization of our experiment. And I just want to point out that it was a group of 6 women, 4 of which were younger than 30, which was kind of an interesting dynamic. Kind of felt like herding cats sometimes. But this is amazing. The first 3 field experiments I did, I was the only woman, and that was 8 years ago. So I just wanted to mention that because I thought that was a really unique aspect of our field program. And yeah, that's it. Thank you. I'll just repeat the question or the comments, and I'll address it. So that was getting to this coherence right here. And kind of this drop-off might just be due to the fact that we don't have a lot of high-frequency energy to go through that prediction. We do actually have some higher frequency events from active source experiments that we have done. But I think what is largely responsible for that is that here we start encountering the as-designed resonances of our structure. And so we really do see a bit of a drop-off in the coherence, I think, because this signal in particular just isn't, it's coupled to the ground. It's not going to do a great job of predicting these resonances. But your point is well taken that we need to look at coherence for a couple different sources. And we have some active source experiments that have sources with a much higher amount of high frequency energy.
Can a seismometer on Europa tell the difference between a conductive ice shell and a convective?
No. But it could probably help constrain temperature. Seismic velocities are often change as a function of temperature, and so the higher the temperature, your seismic velocities will decrease. And so it might help you and can probably help you figure out if there's anisotropy with a technique called shear wave splitting, but it could probably contribute to that investigation, but it would not provide a definitive, I don't think.
You get a temperature profile?
I think through, yeah, you could.
Sources.
I think you could, through inverse modeling, you could come up with one that probably would have it would probably be a distribution. But yeah, it's been done.
Good. You've deployed your lander very carefully, whereas the real lander is just to be dropped unceremoniously on the surface.
Yeah.
Are you looking at different configurations in one leg, not coupled as well as the others, make sure snow and ice or frost and ice, and see how that affects?
We are not. That is it's a good point and well taken. I think I mentioned to you earlier, our seismometer is going to be tilt intolerant, which is good because we don't know what sort of terrain that the lander is going to be deployed upon. But yeah, I mean, that would certainly be a huge hit to the lander coupling to the ground. And so I think if that was to happen, a lot of the other payloads would be in a bad way as well. But it's certainly something to think about. And there's a strong chance that we'll be going back to Greenland to repeat some of these experiments next year. So maybe we could throw that in. Go ahead.
You mentioned at the beginning that you're also starting to look at using seismometers for potential moon studies.
Mm-hmm.
Maybe you could add Mars to that list with the radar Martian study that came out last month, suggesting there might be liquid water at the bottom of the South Pole of Mars.
Yeah, it was actually funny when that article came out. Dante, who I think he had to take off early to pick up his kids, but he sent that to me and said, another location for SIIOS. So yeah, we'll go, I mean, my personal goal is to have this be a payload that LPL can offer to missions and compete for. So we have a long road ahead of us in achieving that goal, but yeah, send it anywhere. I mean, why not?
Is it going to make a big difference if the surface of Europa is just a solid ice sheet versus a like frost and snow, lower density?
Yeah, it'll make a huge difference. So increased porosity usually corresponds to increased seismic attenuation, and this was really very obvious in the Apollo seismic data, which saw a lot of scattering due to the megaregolith on the surface of the moon. And so what that typically means is that you're going to have more noise, and it would certainly impact the resulting seismograms and seismic science that you could do.
One more, maybe, or okay, maybe two more. Back.
Would you be able to see any seismic events from the coal of Europa?
People have claimed you will be able to. I mean, yeah, if you had, it kind of gets back to how large of an event could you potentially have. The paper that I referred to that looked at potential impactors, they cited that as one thing that you might be able to see from a very, very, would be a very uncommon event, but you know, over the course of a decade, you might get an impact that would provide enough energy that you would be able to reflect from the core. And seismology has been used to constrain the core of our Earth and the moon, and maybe on InSight we'll be able to do that on Mars. So it's certainly a fair question. Part of it will have a lot to do with what the actual structure of Europa is, and how warm the ice is, and how much attenuation you get, and just what the largest magnitude event we'll see. So in theory, yes, using seismology we can do that.
Was just asking, like, so in that element side, you mentioned that you have these three layers, the ice, water, and fixed rock. How did you know about these three layers that exist here? There are layers of ice and water that are also formed. It's not really just three layers.
So are you talking about the Europa model, or are you talking about the analog site? So there was a paper done, Palmer et al. 2013, that used airborne radar in order to, they were just surveying that portion of northwest Greenland, looking for, really trying to constrain bed topography. And this is a fairly common way to do that. It's just with airborne radar. And they were the ones who discovered this lake. And so we were in correspondence with that team, and kind of talked to them about their certainty, and were able to look at some of the data ourselves. But we saw it right away through some of our more traditional ground-based glaciological techniques. And so it's actually an incredible analog site. There was not any sort of like inclusions that you might guess. Well, and that kind of makes sense for where it is, what zone it's in within the Greenland ice sheet. But yeah, we leveraged the results from a prior scientific study, and then we were able to confirm that independently with ground-based glaciological measurements.
Okay.